Thank you, John, and thank you all for coming out this morning to hear about black holes. So I'm going to start with a very quick overview of what black holes are, and then I'll tell you about a few of the projects that my research group is working on here at UC Irvine to study the properties of black holes in the centers of nearby galaxies. Now, the basic idea of a black hole is that it's an object whose mass is so dense and so concentrated that nothing can escape from its gravitational pull. Not even light can escape from the gravitational pull of a black hole. And the idea of an object like that, a black hole, actually goes back surprisingly far in history, much farther than a lot of people realize. So the British scientist John Michell in 1784 wrote a letter to the Royal Society in which he came up with the idea of a black hole. And this is an amazing sort of visionary letter, and it's probably hard for you to see, but I'll read you a little bit of what he wrote here. If there should really exist in nature any bodies whose density is not less than that of the sun, and whose diameters are more than 500 times the diameter of the sun, since their light could not arrive at us, we could have no information from sight. So as early as 1784, John Michell came up with the idea that you could have an object massive enough that its gravitational pull could trap light, and light couldn't even escape from it. It's sort of an amazing visionary idea for that time. And he goes on to another really amazing visionary idea here, which he says, yet, if any other luminous bodies should happen to revolve about them, we might still perhaps from the motions of these revolving bodies infer the existence of the central ones with some degree of possibility. An amazing idea. What he's basically saying is that if you have a black hole, you wouldn't be able to see it because light can't escape from it. But if there's another star orbiting around it and you can observe the motion of that other star, you can determine that there's actually a black hole there and even determine the mass of the black hole. And that's exactly what we do today using the best telescopes that we have available to study black holes. So I think John Michell would be very excited about a lot of the work that's going on in astronomy today, since he predicted basically everything that we're doing in this field. Now, to explain the idea of what a black hole is and how it works, let me just explain it in terms of the concept of escape velocity. Suppose you had a tennis ball and you wanted to throw it upwards, and you wanted to throw it so fast that it would escape completely from the Earth's gravitational pull and never fall back down to the Earth again. And let's ignore air resistance and atmospheric drag for the moment and just think about how fast you would have to throw a tennis ball upward if you wanted it to just keep going up forever and never come back. Well, that's the escape velocity from the Earth, which is actually very fast. You would have to have quite an arm because you'd have to be able to throw that tennis ball at a speed of 11.2 kilometers per second to have it escape from the Earth's gravity. Now, if you have an object that is more dense and more concentrated in its mass than the Earth, then the escape velocity gets higher. So if you could, with the wave of a magic wand, if you could compress the Earth to half of its radius, but keep its mass the same, then the escape velocity is higher. Now you'd have to throw that tennis ball up at 15.9 kilometers per second to have it escape from the Earth's gravity forever. If you compress it now to a quarter of the Earth's radius, but again keeping its mass the same, since it's more concentrated and dense, the escape velocity from the surface of that squeezed Earth is now 22.4 kilometers per second. And you can imagine continuing this process until eventually the escape velocity from the surface of your squeezed Earth exceeds the speed of light. And according to Einstein's theory of relativity, no material object can travel faster than the speed of light. At that point, light itself cannot escape from the object.